I'm going to show you how you can, if you have a 3D printer, how you can design a 3D model for a Bahtinov mask and print it. Now, in case you want to know what a Bahtinov mask is, well, you probably already know since that's probably why you got to this video, but anyways, here's some background. It's a kind of a grating that you put in front of your lens or telescope to assist in fine focusing on stars, astronomical objects. So, as you probably know, if you've done any astrophotography, you can't depend on the infinity mark on your lens to set the lens to focus at infinity. So you need some kind of an aid to focus on things like stars. You want the focus as good as you can get it. So what the mask does is cause a diffraction pattern. And if we look on the Wikipedia page, they have examples of diffraction patterns. You can see here's an animation. So as this is now out of focus, but as it comes into focus, there's a bar, this little vertical bar that moves across an X pattern, and when it's in the center, then it's the star is in focus. So how can we possibly how could we possibly make a Bahtinov mask for our lenses and telescopes? One thing is you can buy them, but the ones you can buy are pretty coarsely made, and also they cost a few dollars. Whereas the amount of plastic, if you print it in PLA plastic, it's going to be pennies. It might take, like in my case, it took 3 hours to print one of these, but that's typical for 3D printing. So let's look at how we design it. Well, there's a website, and I'll put the link to this website in the description, and you'll be able to go here. This will create a drawing, an SVG, scalable vector graphic drawing of a Bahtinov mask. And then from that, you have to turn that into a 3D model, and I'll show you how to do that. But let's talk about the drawing first. The basic parameters of the mask is there's an outer diameter, which should be set to fit over the lens, okay, or the telescope. In this case, I'm going to make it for my 200 millimeter. It's an 18 to 200 millimeter zoom lens. I'm going to make it big enough to fit over the lens hood of that lens. So that's, if I remember right, it's 98 millimeters. So we got the outer diameter. We've got this little brim, which is mainly there for support, and an inner diameter with a brim around it. This inner diameter is a hole in the mask, and it's useful if you're fitting it to a telescope that has a central obstruction in the system. So the top of my Schmidt-Cassegrain telescope has a little round mirror in the center of the lens that's at the front of the telescope. So if I were to make this for that, though I've already done, I would have a central circle. But we don't need one for a camera lens. So let's go look at the parameters. So we got focal length that we're going to set to 200. This is all in millimeters. We've got an outer diameter that is going to be 98. We've got the inner diameter of that hole. We're going to set that to 0 because we don't want a hole. Stem width to slit width, we're going to say 1 to 1, so that the stems and the slits are equal in size. And I'm setting Bahtinov factor. Well, let's leave it at 150, and I'll show you what it does. The in width, we don't care because we didn't have a central hole. The out width, I'm going to set to 10. Now, what that's going to do is give me a grating that fits over the diameter of the grating is going to be about 78 millimeters, and that's fine for my lens opening, which takes a 72 millimeter filter. So you say draw mask, and you see, wow, that's quite a fine grating there, and I'm going to doubt that I can 3D print that. This is, on my screen, that's about life size, and that's going to be too fine to print. So we can play with this Bahtinov factor, and if I set it lower and say draw Bahtinov mask, it's a little coarser, but you'll see it's going to be printable. So once you set that, you click on download SVG and it'll download, or you copy and paste this SVG code here into a file .svg, and then you've got the SVG code. The problem with this download button is sometimes it doesn't actually do the download. It just brings you to a page where it displays the drawing, and then when you go hit the back button, you lose all your settings. I'm going to try, what I'm going to do is, just in case, I'm going to copy this code. I'm going to try the download button. Yeah, it's going to allow. Okay, so there, we downloaded it. So what I'm going to do is show you now how to turn this into a 3D model that can be printed. So for that, we're going to use FreeCAD. And if you don't have FreeCAD, I recommend it. If you do any kind of 3D printing where you do your own designs, FreeCAD is a nice free 3D modeling tool that's meant for CAD type stuff. So I recommend it. It has had some bugginess, but overall it's a good thing to use, though sometimes a little cryptic in, like, what am I exactly supposed to do to try to do what I want to do? So it's hard to get information about how to use FreeCAD, but here I've done the work for you. I'm going to show you how to use FreeCAD. So I'm going to go over here, and you can see I already have one that I designed up. So we're going to I'll go through the process from scratch. So we'll create a new, they call application, and we're going to go to File, Import, and I'm going to import, this is where I'm keeping all my stuff. I already saved that file as finer for 200 millimeter lens.svg. So I'm going to bring it in. Now, the first thing it's going to do is say, do you want to bring this SVG in as a drawing or as SVG geometry? You want SVG geometry, and then you say select. And then it's going to ask you about the resolution. It's expecting that you're using Inkscape, which is another free program for making, it's a program for making SVG drawings. But it wants to know the units. And it's going to, if you say yes here, it'll use 96 DPI as the units, and that's appropriate. So we say yes. So now it brought in the drawing, and if I take a look at the top view here, you can see that it brought in a bunch of individual paths that we can't work with. We need to combine these into a sketch that we can extrude. So what we're going to do, the magic is you select all the paths and you go to the draft workbench and you go and find this tool that looks like a sketch. It's got the little red lines like a sketch, and that tool is draft to sketch. So we click on that and we wait a little bit. And now it's done, and you can see it created a sketch. Now, the sketch has the whole drawing in it, and we can get rid of these paths now. So on a Mac, it's function delete to get rid of those. Now we've got the sketch. Let's go to the part workbench, which allows us to extrude plain sketches. So unlike the part design workbench where you need an object with a sketch inside, part workbench allows a sketch on its own to be extruded, and this is the tool, extrude. So we'll go to extrude. Now I want it to be pretty thin because I want this to work as a diffraction grating. So I'm gonna pick 1 millimeter down here for the length, which is the thickness. You don't want it too thin, or otherwise it's gonna be easy to break, probably come apart when you remove it from the print bed. And you don't want it too thick because what you want is sharp edges. So in order to cause diffraction, you need sharp edges. So we say 1, click OK, and there we go. We got a Bahtinov mask. But we want some help here to attach it to the front of the lens. And what I did was, if I go up here to create tube, I will say the inner radius should be the radius of the mask, which is half of 98 is 49, and the outer radius I want it to be 2 millimeters thick of a collar. So that would be 51. I recommend putting in the 51 first so that we don't get weird looking stuff happening, and then the 49. And then as far as thickness, it depends on your lens, how much height, how high do you think it needs to be to get a good grip on the front of your lens. And in my case, let me just put 20 here just as an example. So what I did, so that's the mask. All right, let me just show you what I did over in my one that I actually made. I made the height 37. My lens hood on my 18 to 200 millimeter lens is what do you call a pedal design. So it has to be long enough. I didn't want any stray light to come in the sides, so it has to be long enough to cover the pedals. And so I could update this and go down here and say 37. Okay, so now we've got the mask. Now you could go up to File, Save, to save it for future use. But if you want to get your model for printing, you would do extrude. You would select extrude and tube. Go to File, Export, and export an STL file. So I'll show that. You would basically select down here STL mesh and give it a name and say save. So now I should show you Cura. So I should show you how you would load this if you're using Cura. If you're using a different slicer, it will be similar, but I use Cura. So I'll show you an example of loading it into Cura and checking it out to see if it will in fact print. So here's Cura, and you can see I'm set up right now to use my Ultimaker 2 Plus, which is a great printer. I actually bought it as a 2 and upgraded it to a 2 Plus, and it's been working wonderfully for almost, I don't know, 10 years, almost 10 years. So if first thing you do is bring the model in, and this is the one that I made, and we want to see if this grating is gonna print, or it has a chance to print. So I'm using, for a profile, I'm using a calibrated profile, one where I calibrated it for the size of holes and the size of things, and you do that so that things that need to fit into things fit. If you use the default profiles, at least on this printer, if you like make a round peg in a round hole of the same dimension, it's not going to fit. Whereas, and so you have to play around with making them different sizes. Whereas if you bother to calibrate the thing for hole sizes, you can get it so that you can make the peg and the hole the same diameter and they will fit into each other. But anyways, so this profile has been I call it PLA Pro compensated. I'm going to be using PLA Plus, which is really the same thing as PLA Pro. But the other thing that I've done is I adjusted for elephant foot. And what is elephant foot? Well, this printer, you manually set the bed level with basically to the you set the distance, the 0 point of the z-axis. You set it to be a paper's width away from the bed, and you have 3 thumb screws, and you adjust those manually. Now that means that the distance at 0 is going to be variable. Okay, it depends on how you set it, and I always use the same type of paper, and I get a certain distance between the nozzle and the print head for layer 0. However, what happens is it's not going to be the same as printing subsequent layers, the distance between the head and already printed plastic. So there will be a difference in the amount of squishing that the little spaghettis, the threads that come out of the nozzle. So on layer 0, there may be more squishing than on other layers, and that gives the effect of, if you print a peg, the first layer of it will have a little bit of a bead around it after printing, and so it'll be a slightly larger diameter, even though you calibrated the diameter of things. So that will also make it difficult to make parts fit into parts. So there's a compensation for that, and I think it's this one here, initial layer horizontal expansion. I go negative 0.25 millimeters to basically thin out things, the outer edges of things on layer 0. So let's do a slice, and you can see it's going to take 2 hours and 29 minutes. And let's do preview and see what we have here. We're up here at layer 185. Bring it down to layer 0. And, oh, okay, so it's not printable. Let's take a look. So you look at layer 0, and you see that because of the thinning of things for both getting the size of holes right and elephant foot, it's really not printing anything for the slots. So what I did was put the initial layer horizontal expansion to 0 so that I'm not compensating for elephant foot, because it's not actually necessary. And here now we see that I'm going to get 2 threads wide. So the slots, the solid parts of the slots are going to be 2 threads wide, and that'll be printable. So it's important when you design your mask and decide how fine you want to make it, that you bring it into your slicer, slice it, and look at layer 0 to see if the slots even show up and if they're going to be printable. Like if I make this finer, then I might only have 1 thread per slot for the solid part, and that might print, but it might not be very strong, and it might break even trying to get it off of the build plate, which is in this case a glass build plate, a heated glass build plate, and I've got glue stick, and it's generally hard to get PLA plus off of that, even if you let it cool completely. Sometimes you could try freezing the thing to get it off, but basically I end up using a little bit of a prying tool to just pry an edge, and then it will pop off. In the case of this particular model, it came off, and it felt like there was a little flexibility in the grating, but it survived coming off the build plate. This is what you need to do when you're making a fine thing, a fine grid like this. So if you go in and design a different grid, I suggest you bring it in to your slicer, slice it, look at layer 0, considering your compensations, all your compensations in your profile, and if necessary, make adjustments to the profile to make it printable. And that's it. And then I have a little video here where just to show that it was printing, and that's the how-to. Now, does it work? Well, I think it does. Unfortunately, last night it was relatively clear out, but I was exhausted from staying up the night before taking photos. And so all I could do was at about 9:30 go out and try to take some moon photos. Now, this mask, you can't focus on the moon with this mask. The moon is too large in diameter for you to see a diffraction pattern. So it's nice and bright, but too large. So you need basically a bright star to use this mask. Now, what I did do just to test and help me focus on the moon was I used this mask to focus on a street light way down the street. Okay, so approximately at infinity. And in the case of a street light, it's a small enough round bright light that I was able to see the X pattern and the line as I showed you in that Wikipedia page, and I was able to focus on that street light, and then leaving the focus set, take a shot of the moon, and I got a reasonable focus. I had other issues going on that made it so that I wasn't getting a very good focus anyways on the moon. Number one, that street light is not really at infinity. Number two, the moon is moving too fast for the shutter speed I was using, and so I needed to put it on my tracker, but I am currently waiting for a delivery for a finer lead screw for my Astro tracker, so that I can the 200 millimeter lens is heavy, and I need a finer lead screw to see if that helps, so that it actually will track and not just skip steps on the stepper motor. So that's the story. I hope this is helpful. You really do need some kind of, I know I do, some kind of focusing assistance for astronomical photos, because the requirements are high. There's a high requirement for sharp focus, and being in low light and having dim things that, yes, you can make them brighter in live view. It's hard with an eye, especially an eye of my age, in dim light, to do any kind of manual focusing. So you need, you could put your camera in live view, aim it at a star, and focus it until the star is the smallest dot possible to try to focus. But this will be a little more accurate. And by the way, when you do this, you use live view because, again, a star is not bright enough in an optical viewfinder going through this mask for you to see the diffraction pattern. So what you do is you put the camera in live view, aim it at the star, get it in the center, and zoom in to the star with live view, put the mask on, do the focus. Okay, so it's going to be a combination of live view, zooming, this mask, and manual focus in order for you to focus on stars. Okay, now that's the end of the how-to. Thanks for listening.